Hi everyone, what I have today is a Toshiba Satellite C655 model laptop. I'm told that the battery has been replaced and the charger power brick has also been replaced, and there was problems with the thing shutting down randomly, turning off randomly. I'm not sure if it's an operating system derived shutdown or if the whole thing just went dead, but it's been handed to me in a state of it won't turn on anymore and there's no light on the front. So I think basic initial tests we can do. Pull the battery out for a start. Sometimes these laptops shut down if something goes a bit screwy, and or they think they're in a hibernation state or something, and until the battery is removed and it forgets that fact, it can appear to be dead and not turn on and so on. So I think the first thing we'll do is pull the battery out, give it a minute or so to drain, and I don't think I'll plug the battery back in. You can run laptops straight off the power bricks, so I'll also test that there's power coming out of that, and then we'll plug that in on its own and see if the thing responds to that without the battery in. Alrighty, we shall test the power brick, which is 19 volts, and we have 19 volts. There's a good start. Now I've plugged it in. On the bottom corner here there's a couple of lights, one to indicate when the power's connected. We have nothing there. I'm just going to wiggle the plug while it's in the side of the laptop and just see if it comes on, because these have been known to dry joint and give you a bad connection on the motherboard. I'm not seeing anything there, so it's either broken too far off or it's not that. And of course, as a result, pushing the power button does absolutely nothing. So we obviously have an internal fault. Let's get this thing apart. Okay, just to show you what I could feel when I was doing that, there's if I grab that center pin and give it a wiggle, there's quite a bit more slop than I would like. The entire socket's moving, not just the center pin. So cross fingers, that might be all it is. Well, I've got all the screws off the bottom, and Toshiba were nice enough to make them all the same length, so they're not going to be an issue if they get out of place. The next thing to do is the keyboard. Now I've just slid a fingernail around the edge, and it has unclipped the entire keyboard and frame, but the keyboard actually needs to come off separately first. Now I think this strip along here is going to lift off and allow access to that. There we go, just a little bit of pressure and I heard a click there. Just run that along. There's another one. Another one. All the way down to the end here. There we go. And that's given me access to, there's 4 screws holding the keyboard down. Once they come out, we'll be able to unplug the keyboard and the outer frame will be able to be removed. Right. Now these screws are quite small and different to the ones used on the bottom of the case. I remember much earlier laptops, there'd be about 3 or 4 different length screws, but it's good that they sort of wised up to that, I guess. also the cost of having to carry all the different size screws when assembling it made it just a better to use the same length screw, as well as ease of service. Now there's a ribbon cable down in here, and that's going to have a bar that goes right across there that needs to slide up, so it's just a matter of lifting in the corners, one there, one there, and just very light pressure until it gives. If you push too hard and snap that bar out, they can be quite annoying to put back in. Sometimes they don't even go back in, so you have to find a way to reattach the ribbon cable. Just a little bit of a, oh, it's just tucked underneath the plastic there. Done. Now a slightly different style of connector, this flat flex coming down from the trackpad, mouse pad, that just needs to lift up like that, flip up, and once that's free you can just sort of lift the frame and that will come out with it. Now I have just noticed, before I get too carried away, there's another plug over the back here. We'll have to wiggle that off. That's going to be our probably our speakers. There's another little one over here which I think is going to be the power button, if I'm guessing. We'll know when we get in there. Just a little push. Maybe we can pull that off now. There we go. Voila! One mainboard. Oh, that's unfortunate. Or fortunate, depending on how you look at it. But it does mean a bit more video, because there's our DC jack, and it's loose because that's how it's made. It just sits in there, and the wires come off over to the main board here. So it's not a fact of a bad solder joint on the main board, on the DC jack. So now we get to delve a little deeper, and it's fairly clean looking as far as the heatsink goes. I don't think it's suffered any overheat or anything like that, but there is a bit of dust floating around. Okay, let's have a nosy at where we can take some measurements. First thing I'm going to check is the little CMOS memory battery here, little coin cell. I would have the meter in shot, but you'll have to take my word for it. I really need a taller tripod, but we'll just check, make sure that that's got 3 volts, and it does. I have seen dead batteries prevent systems from starting up before. I think what I will do too is just remove that so that it can give it a bit of a reset. But no, I actually don't think that's going to help at all. There's no light on the front to indicate that the mains adapter is plugged in, and that would be completely independent of any BIOS function, so I'm going to leave the battery in there. So looking over here, we'll try and follow our way through the circuit as far as where the power goes, and let's get that out of the way. We have our power coming in here. There's a fuse there, likely the main fuse. I will check that, make sure that it's good, and I'll put it on beep so you know that that's a short circuit, so you also know when I do that it's good. And fuse is good. Okay. Now I've plugged in the AC adapter, and we'll see if there's any voltage getting through to the fuse. Now I guess this should be ground here. Looks probably like a ground, although the traces aren't going directly to it, but we'll find out. I'll put power on there, and we have 18.7 at the fuse, so that's all. Should be enough. I know this thing requires 19 volts, but yeah, I don't think it's going to be an issue. Over 0.3 certainly should be enough. Let's keep looking through from there. I'm going to have to take the board out to get a closer look. There'll definitely be something on the underside, all of the voltage regulation on the underside. There's not a lot on top, as you can see. So that seemed fairly easy. There was only one screw here, as marked with a little white triangle, and the fan, which had 3 screws around the outside and a electrical plug, that just flipped out. There is a reasonable amount of dust build up along the inside of the heatsink vent, not enough to stop it, but not ideal. But now it looks like the whole thing's free. We should be able to whip that out. So fairly straightforward laptop construction. The main CPU under there, probably graphics chip under there, and RAM, battery connectors down here, and this is where all of the power regulation is done. So this is where it gets interesting. We have the main power supply connector, charger connector comes in through here. Just having a look over here, I'm pretty sure this is going to be the battery charging circuit. You can just see a fuse with the gold ends and the white sneaking in behind the connector there, so we'll have a look at that fuse, check that, but that'll be the battery fuse. Probably not an issue at this stage. Now coming up through here, we have the constant beep of my meter turning off. I really should disable the auto power off. But we have up through here what looks like, I bet these little ICs here are going to be the switching control ICs that would run these, which will be FETs that'll switch power through these coils, which will give us all the different voltage rails. Fairly common use of parts there. This one over here, I think, being slightly larger, I'm pretty sure that's also a switching controller, but you know, we'll go in for a closer look and have a look at the data sheets too. But I think this is where our problem is going to be, as there's nothing showing up on just the very basic LED to say that power's going in. Alrighty, a quick Google search reveals that, well, the number on here is a BQ725, and a search brings up a BQ24725 by Texas Instruments, is a lithium-ion battery charge controller. And what else has it got? Advanced circuit protection, uses N-channel MOSFETs and so on. Which makes sense because it is in proximity with the battery connector. Now if we have a look down here, we can see we've got what looks like a power FET. It has 8 pins. 4 on one side are all joined together, and 3 on the other side are all joined together, with 1 as the control on-off line, and that's a very common package you'll see in these setups here. We've got another 2 over here. They're actually doing switching of this inductor here, but in this case we've got a couple of smaller ones doing the switching, and this is our I'm gonna take a guess that what happens is this feeds the laptop from the battery, and when they want to charge the battery they actually turn this off so that they can charge the battery and maintain the laptop power off the AC adapter. When AC adapter is lost, this turns on again and powers the laptop through here. It would obviously be self-defeating to try and charge a battery while you're drawing power off it at the same time. So this is with all likelihood our battery charge controller, and I'm not too worried about that at this stage. But what we will do is see if we have our input voltages as per the data sheet, what it suggests they should be, and see if they exist. Moving up here a little bit more, I'm gonna hazard a guess that this is one of our voltage rail controllers. It switches these two FETs across this coil to produce one voltage rail. There'll be something switching these two FET packages. Again, an 8-pin package with 4 on one side and 3 on the other as our input and output, and 1 pin as a control. That may be controlled off here as well. I have yet to look up, see if that's a control IC. I'm just going off proximity here. There's every chance that it could be entirely all of this controlled off this one up here, given it's much larger, but that may be for other things. There's also another voltage rail here. So we've probably got something like, I don't know, 5, 3.3, 1.7 or something. It doesn't appear to be marked on the board. That would be far too generous of them, wouldn't it? If I send your eyes up over here, we have some more inductors. Now these are going to be the CPU voltage rails here, and probably GPU voltage rail. This looks entirely like a control IC for the switching of those voltage rails, with all likelihood that it does the GPU as well. So let's start probing around back down here, see if we can see where there's power, where there's not power. I think it's time to pull out the old scope. That'll pick up very slight fluctuations in whether, we're going to look at the drive to these, see if they're trying to start up and failing. We'll look at things like whether there's low resistance on the across these capacitors. These are our output capacitors. Given the size of them, they would be the main supply for the rail generated. Okay, and here is a picture of the battery charge control IC. As we can see, we've got VCC at pin 20 on the top left. That's where our voltage should be coming in. Ground is pin 14, which is second one down on the right there, and this is a quad flat no leads QFN package. So lucky we've got traces to external components that we can probe on, because getting your meter lead on those pins is just asking for disaster, having it slip and short out to the pin next to it. So what I'll do first is an old resistance test, and we will see if there's any low resistance on these output capacitors. So just figure out which side's. Pretty sure ground is going to be on the other side there with the stripe. Yeah, that's ground. So okay, the stripe's got ground on it. So here we go. First rail of the day. That's giving us about 500 ohms. I wouldn't have thought that would be too low. Second one there. What do we got? Yeah, over 10k. That's plenty high enough to be happy. Now third one here. yeah, over 20k ohms. So compared to this one here, then you could argue this is just a little low. I know I've seen a few hundred ohms before be okay. I've also thought that that would be okay and found it not to be okay. So it'll be interesting to monitor the gate pulses on these, see if this rail's coming up or not. May find out that it's actually not. Right, now let's see if we've got power to the charge control IC, and we'll go from, we know that these are ground, these large exposed copper circles, and we have down here a surface mount capacitor that has a lead to pin 1. So if we have a look on there, we can see we've got 18.6 volts, which is our incoming voltage. If I probe on there just to prove that, 18.9. So yeah, so we know that there's power on the charge control IC. I'm just going to probe the battery fuse just for the hell of it. We've got a volt on there. It's obviously not being charged at the moment because there's no battery attached. Okay, so now what we need to do is we'll see if there's any voltage rails being generated. We'll start with the output of this capacitor here. As we can see, there is absolutely nothing. We'll check this one here, and we have nothing there, and we'll come up to this one here, and again no rails being generated. So at this stage none of these are working, but I would expect at least one should be working, and that would give us our standby light or AC adapter plugged in light. So let's just do a little bit of a quick finger test to see if everything's getting hot. Everything's pretty stone cold. Right, I think we'll move on to the scope and see what these gate pulses are looking like. Okay, so what I'm going to do now is probe the gate pins of these power FETs here, and it's this pin here on this one, and then the other one's flipped upside down, so it's this pin on the bottom corner here, and that's where I'll be probing. And I will do the same with these little ones up here, and these little ones up here, these two here, that switch that inductor, those two switch that one. These are bigger, that's obviously a higher power rail, and we'll see if any of these are trying to start up at all. Okay, so we'll probe the first one. Now these work in tandem, so if I've got signal on one, there's guaranteed to be signal on the other one, or almost guaranteed, I suppose. We probe on that one there, so I've got nothing there. Let's see if we've got voltage rail here. Nothing there. Nothing there. So we actually don't have any voltage on that coil for it to switch in the first place, which is interesting. So if I probe the input, I've only set to 1 volt per division, and it goes right off scale, so there's definitely scopes working as it should. And if we probe the other FET, oh look at that, so I've got power on one FET there, but I've got nothing on the other one. Now thinking about it, one of them switches power, the other one switches ground, and they work in together. So yeah, alright, my mistake. Okay, so we'll check still the gate pin of the one with power on it does not show any signal at all. So we'll just try for the pin on the smaller one there. We've got nothing there. We'll go for the other last rail up there. We appear to have nothing there. Now I'm just going to drop. What are we doing? I'll just drop down to a really low voltage to see if there's a very faint trace of some sort of signal there. Looks like something, but it's I wouldn't really say that was. Yeah, it kind of looks like something, but it's very small. That's at 2 millivolts per division. That could just be garbage. That could just be real garbage. Nothing really meaningful. Something similar on one of the other rails. Yeah, it looks like the same signal. Not entirely convinced, to be honest. I wonder if it's coming through off the power supply. Let's channel 1. Here we go. We'll just AC couple that and see if there's what's on the actual power supply itself. Yeah, bugger. It's kind of dancing about similar. So I think what we saw was noise just coming through off the charger power supply AC adapter. So just doing a bit more research, this IC here has got the number 51123 written on it, and a Google search showed nothing, suspecting that was a step up, step down controller, switching IC, controller IC, and suspecting that these were. I noticed these ones have a similar number with TPS in the front of it. So this one here is TPS 51460. So putting TPS in front of here, and I get it's a Texas Instruments, again dual synchronous step down controller with out of audio operation. So I can only presume out of audio means that it'll switch the inductors such that it doesn't make an audible buzzing noise. And here is the data sheet. That's exactly what we're looking at there. It's another QFN package. Operates over 5.5 to 28 volts. Output voltage range of 2 to 5.5. And lots of other goodies. Particular applications. Notebook computers. What we need to do is find out if this has the rails that it needs to operate on, and sort of we'll have to read through the data sheet and find out under what conditions it does not operate on. So it's obviously managing any fault conditions, and it won't start up if it believes that there is a problem, as much as a IC can believe anything. So let's check the voltage input pins and see if it has what it should have. So we're looking at over here, what have we got? 5 volts there. That's V out 1, V in 5.5 to 28. V in. Okay. Don't believe that's not the IC power. Okay, hang on, keep looking. We've got V in on pin 16 mentioned. Okay, here we go. Yeah, so we've got V in up here, 5.5 to V in, pin 16 to V in. So pin 16 should be 5.5 or more for this to operate in a stable fashion. And then our driver outputs, okay, it's rigged up to control one inductor to give a 5 volt output and another one to give a 3.3 volt output. Looks like a dual power supply rail regulator. Alrighty, so where I'm going to probe is onto pin 16 that was marked V in, and we'll see what that's got coming. And pin 16 goes to this larger surface mount capacitor here. So with any luck, I'm going to get a reading of 8.5 volts or more. Angle my meter so I can read the thing. And what have we there? Okay, it doesn't look so flash. It's fluctuating from 6 to 8. It's all over the place. It's not very stable at all. I'm going to put the scope on that and have a nosy. Right, get back on it. Here we can see a oscillating voltage there with a minimum of about 4.8 up to a maximum of about 10. So it's I'd expect it to be a lot cleaner than that. Need to figure out what's deriving that voltage. I think I've found where the voltage for this IC is being derived, and it's almost definitely controlled by the battery charge control IC. It must also have its fingers in the startup power control. If I flip the board over, we can see two other power FETs on the bottom. They are actually connected in series with the gates tied together so that they operate at exactly the same time, and our voltage that we saw just before is coming off these. I think perhaps what we could do is have a look at that voltage in on that IC, and just check the resistance on that line and see if maybe it's a bit low and is overloading the input to that IC. So go resistance to ground off of the large capacitor. Of course the power is disconnected while I'm doing that, just out of curiosity. But showing 7 meg ohm across there. So back at the lovely data sheet for the charge control IC is also the input selection IC, so when AC is present it switches off the battery and charges it, and when AC is lost it reinstates the battery. And quick overview here, we've got our AC input connector this side, comes through. There are a couple of FETs there, which are the two that I alluded to before. This laptop seems to be, this is the data sheet, so it's not the exact circuit diagram in the laptop, but the manufacturers seem to have stuck with it for the most part. So we've got two FETs there, and we've got an AC drive on FET, and this other one here, which yeah, they're in series. Anyhow, once AC is detected and certain conditions are met, there's a pin here which gets pulled low to indicate to the rest of the system that AC is present and is okay. Over on this side here we have our battery connector, and that's we've got the two FETs here across this inductor which generates our charging current, and up here we have the isolation FET, which I'm picking will be the big one on top that I showed earlier, and that switches the battery in to the system or out of the system for charging purposes. Marked battery drive there. So we've got our AC input, adapter input comes straight through out to the system. And quick battery change, where was I? Our AC adapter input straight through the FETs out to the system, and failing that, when AC is removed, this FET's turned on, which comes up and out the battery power out to the system as such. Now the battery voltage is only 10.8 volts. It could explain the ripple voltage that we were seeing generated here. It's possible explanation. Another possible explanation is it, for whatever reason, can't detect that the adapter voltage is suitable, and could be just switching on and off in response. So we need to have a closer look at the conditions that need to be met for this thing to turn on solidly and send power out to the system. Having a look at the other regulator IC, we know that the input voltage could be anywhere from 5.5 to 28, and our AC adapter voltage is 19. So there's every chance that that ripple that we're looking at should actually be on all the time, and just a solid 19 volts. We know that this IC can handle that. So I'm pretty sure then our problem lies with this initial IC here, and it's not starting up for some reason. Further down the page, they've got some great screenshots of a scope monitoring the waves, the voltage levels at various stages of operation, such as, here we go, voltage in, AC detect goes high when the AC input is active, AC OK should go high a short time after that. There's also a low voltage dropout regulator voltage, which I think it said was about 6 volts, which is used for in the event of an AC dropout or say a brownout or what have you. It gives it enough time to switch back to battery, and various other waveforms according to what state of operation it's in, whether it's in charge or running off the battery. But so far the one that we were looking at doesn't quite look like any of these, so let's get back to the bench. So I'm going to probe pin 5, and that's the bottom corner pin here. Now I have no problem in doing that because it's the one on the corner. I've got none beside it on one side to short it out, so I wouldn't do this with if there was a pin either side of it, but it's quite safe to do this. And we're going to see if the AC OK signal goes high to tell the rest of the system that it should be okay to turn on. Right, now I'm going to single-handedly, since I've only got 2 of them, plug in the DC. Okay, as we can see, the AC OK signal is not happening. Let's make sure I'm on that pin properly there. Very, very small pin. Now it should be high, and it should get pulled low. I may be missing it. It may be happening a bit too fast. Okay, slight back step then. We'll look at the AC detect pin, and according to the data sheet, it should be between 2.4 and 3.15 volts on the AC detect pin as obtained by a voltage divider off the direct AC input. So we'll make sure that that's working and there's a correct AC detect voltage on that pin. And that's going to be on pin 6, which is we've got 1 through 5 down here. 6 is the next one around the corner. There's a little solder blob right there and another pad that we can probe on. We are at 2 volts per division, and I'm connecting AC now. And we're just over 2. We're at 2.2, 2.3. So we have AC input voltage on that pin. That side of it should be working. Let's have a look at the other factors that affect whether AC OK goes high. Okay, so the other factors here, when the AC detect pin is above 0.6, we just saw that it is. It's about just over 2 volts. The undervoltage lockout, the reg N, which is the low voltage dropout regulator voltage, is present, and the AC OK comparator are both active for AC detection. Okay, so we need to check the undervoltage lockout and the low voltage dropout regulator. Make sure that that's functioning properly, not giving a false signal, because we know there is no low voltage. It's coming in at or just under 19, which is plenty. Okay, so the REGN low voltage dropout regulator input signal is pin 16, which is off the end of this capacitor just here. So I'm just going to probe that one and see what we got. Okay, and we're looking at 246 volts, so that's at 6 volts, which is what it should be. So that's proving that okay, we've got the 6 volts, we've got our 2 volts on the AC detect signal in, so there must be something else causing this to not start up and maintain power. So in the sample circuit diagram we have there's an AC input FET and a reverse blocking FET, and that has to do with the reverse polarity input protection. So one of these is going to be our main AC input FET, the other one's our reverse blocking FET. They run in series, and in the sample diagram there's another FET somewhere that has to do with protection of reverse polarity input. I'm not 100% sure which one that is, but this one here is definitely going to be our battery enable FET, and as it's straight in line with a fuse to the battery, of course. And looking at this, we've got our charge inductor comes through this resistor here. Bet your bottom dollar that's a current shunt, and it uses that to monitor charge current. And yeah, so okay, so what it's doing is it's sort of cycling our AC input FET as we saw. Still not 100% sure why that is, this stage. Okay, the AC OK line is only going to go high once the power supply starts up and provides a 3 volt rail there, so we're not going to see the AC OK line go high until this thing switches on the main FETs. I'm wondering if this is going to be a good time to test the FETs. What are the chances that this ramping oscillation that we're seeing is because it hasn't started up within a certain time frame, it's shutting down and to try again. We're pretty sure it's not an overcurrent sense, as we just checked to ground the resistance on the output of those FETs. So I guess if one of those FETs isn't working as it should, we could be seeing something like that. I think I know what it is. What we're looking at with that waveform on the AC drive on FET. Now, I think it's an inrush current protection. It's ramping up to, we saw about 10 volts because we know the battery's 10 volts. But anyway, it's ramping up. It's getting to a point where this has enough voltage to turn on, but that's not happening. So we're not getting our 3 volts on the AC OK signal, so it's shutting down. and then it's trying again. That sounds entirely plausible. So I think we need to shift our focus now to the rest of the power supply and find out perhaps why that's not starting up, and that I think when we figure that out, that'll turn on and that'll allow that to stay running and do its job. Well, it's another day, and look what I've got. Green light. And I actually didn't do anything other than get an electric shock to make that happen. Yeah. So what happened was I was still probing around over in the input side there, and I was touching the grounding of the PCB. At the same time, I unplugged the well, that was attached to the scope lead, which is ground. At the same time, I unplugged the plug for the laptop and touched the side of that, and got a bit of a tingle off that. On taking a measurement, I find that it's 100 volts above ground. Yeah, and I'm pretty sure these output power bricks really shouldn't be floating their output that high. Now I know, yeah, okay, so the laptop will never know, and you'll probably never feel it because the case is plastic and so on, and it probably shouldn't really matter because there's still 19 volts on the output, no potential between the two there. But I think it might have been interfering with something, and yeah, after receiving that shock and playing around a bit, the light just started coming on. I don't know if it kick-started the motherboard or what. It sounds a bit stupid, really, doesn't it? But because I did feel it through the ground of it, and I could have been touching anything at the time. That said, it seems to be behaving itself, and when I throw the scope on the input selection FETs, instead of getting that varying waveform that we were seeing, I'm getting a solid DC out. The gate drive is on, turned fully on, about 15 volts. The output is coming through at about, well, let's have a look. So we've got the first FET in the line is turned on. We've got 19 volts coming through there, and the second FET in the line is showing 19 volts as well. Now if I slot the battery in, it should go into charge condition, and the light turns orange. Now the laptop's not turned on at the moment, it's just in standby. And if we check the battery terminal there, that's showing 11.2 volts, so that is higher than the 10.8 it's rated at, so that's showing that it is charging, which is good. And we've got 17.6 volts there now, but I guess that's a bit of load for you. It's drawing. I'm actually running it on the bench supply instead of its own power supply. It's drawing 1.96 amps. So yeah, I'm going to leave that on and see if it charges the battery. I'm starting to think that there's nothing wrong with this unit at all. I'm thinking that the AC adapter is spitting out shit that's upsetting it. Yeah, I suppose we could. Well, I don't really want to scope the line. I'm shorting 100 volts to ground through the scope. I was doing that before anyway. It hasn't killed it, so I could probably scope the output of that power supply and just see if it's got some nasty waveforms on it. Could have been very well upsetting the logic of this thing, given that there's some intelligence to the input control chip. It wouldn't take much to upset it, I think. Well, it's all back together and working as it should. I guess the takeaway from this is things aren't always as they seem, and don't trust cheap Chinese poorly manufactured power bricks. It might have all the certification stamps along the bottom, but I could almost guarantee you that it's just a picture and they haven't had any certification approval. Well, thanks for watching, and hopefully you might have learnt something. Certainly studying how the switch mode ICs work and what's required to get them running, quite interesting. I'll link in the data sheets below, and call it a day.